Hi guys, today I'll just give a small demonstration regarding Norton's theorem. In my earlier video you would have seen the application of the Thevenin's theorem and the Thevenin's theorem itself, where I would have explained the purpose and how to apply that in a given circuit. Now in this session we will see the application of Norton theorem and its definition. By definition it is similar to the Thevenin's theorem, where you have a resistor connected in series with a voltage source, but here the difference is we are having a current source connected in parallel with a resistance across the two given points of our analysis. Now this theorem, while being stated, it might be just like any other definition, but in order to illustrate that with this given circuit, it will be more helpful to understand the real application and the meaning of the theorem itself. For now, you can keep one thing in mind, that this resistance which is connected across the current source is nothing but the resistance of the entire circuit. This resistance may represent the resistance of the entire circuit across any given 2 points of our consideration. We may consider any given 2 points in the circuit. Those 2 points may be across any particular element, say for example a resistor whose values changes, or a capacitor whose values changes, or an inductor whose values changes, or any combination of these three whose values may change. Now the element whose values are changing affects the entire circuit. You can keep that aside and assign 2 points A and B across that variable element, and the rest of the circuit can compute the resistance of the entire circuit and for the rest of the circuit, and represent it as the Norton's equivalent resistance, which is nothing but the Thevenin's equivalent resistance, since the computation of the resistances are the same, and the current source is nothing but the current flowing through that variable element of the circuit, and now that is computed using any analysis of the circuit, say for example mesh analysis or node analysis. We'll see that later, but this current source is that current which flows through the variable element of our consideration, and it is placed in parallel with the equivalent resistance of the entire circuit except for that variable element. And when these two elements are placed across those 2 points A and B, the variable element can now be connected back to the circuit as shown here. Here I have considered a resistance whose resistor whose resistance varies, which is called as rheostat, just as in Thevenin's theorem I considered. Now this is the variable element in the circuit across which we are connecting the entire circuit's equivalent resistance and the current source. This is nothing but the current flowing through this particular element in parallel with this particular element. So we are placing these two in parallel with that, representing the entire circuit. So the entire circuit is reduced in such a format. Doesn't matter how big or how complex it is, it can finally be reduced into such a format. So this is what the theorem states. It states that any given electrical circuit can be reduced into an independent current source. Now this is an independent current source called the Norton's current, connected in parallel with an equivalent resistance called the Norton's resistance, same as computed in the Thevenin's resistance, placed across any two given points of the circuit. Now those two given points of this can be any two given points in the circuit, which is mostly the points across the variable element. Now that's what I have stated in the application. Now in the application what I have stated is that sometimes in a given circuit one particular element, say for example a resistor or a capacitor or an inductor, as I said a while back, any of these element or any of the combination of this element may vary or may not vary. If it is varying, you keep that aside and compute the resistance of the entire rest of the circuit and the current flowing through this variable element. You can keep these two parallel with those points, and then compute the total current of the circuit flowing through that particular variable element for specific values which keep varying. So you need not analyze the circuit entirely for each and every time the variable element varies its value. So we'll see what circuit we will be dealing with in the entire actual practical case. Here we have a circuit, and in this circuit entire given circuit you have a capacitor whose value has a variable range from 10 picofarad to 20 picofarad. This is nothing but pico symbol. 1 picofarad is nothing but 10 to the power minus 12 farad. So the range is 10 to 20 picofarads. Now this capacitor actually changes the values. For each change in the value, the entire circuit changes. So for each and every time we cannot keep on repeating the analysis of the entire circuit. Say for example, keeping the value of the capacitor as 15 microfarad, you compute the branch currents at different branches. What are the currents flowing? It will change when you perform a mesh analysis for that particular value. Say for the next experiment, the value of the capacitor is changed to 17 microfarad. Now 17 picofarad, sorry. If you change the value to the next variable, say for example 17 picofarad, then again the values of the current flowing through different branches will change. So for each and every time we need not conduct the mesh analysis for the entire circuit. So that is what we're doing here. Putting aside this particular variable element here, it may be a resistor, a capacitor, inductor, and computing the resistance of the rest of the circuit. So apart from this, the rest of the circuit has a resistance that we will compute, and the current flowing through this particular element, which is nothing but A and B, the current flowing from A and to B or B to A, the current flowing between this 2 points across this element, that we have to find. That is nothing but this current source. If you place that current with, in parallel with the resistance of the entire circuit apart from this variable element across this variable element, then this is what would be the equivalent circuit reduced into. So we are primarily going to reduce this entire circuit into such a format. So this is what the theorem states actually. In a given electrical circuit, doesn't matter how big it is, it can be reduced into an independent current source and a resistance placed across these 2 points, which are our consideration. So here we are considering this element as a variable element and marking these 2 points A and P. Across these 2 points we are supposed to find the resistance and the current flowing through the element across these 2 points. Now let's just find the current source. The computation of current source is nothing but finding the current flowing through the variable element here. So in order to find that, we have to short this element using a simple wire and see how much current does it flow. You can have an actual piece of a circuit, a printed circuit board, and connect all the resistance in the particular arrangement here and provide such voltage sources and current sources and test for the value by shorting this element. You just find what the current would flow through this particular wire if it is shorted between the 2 points A and B. That is what would be the current source. Now, we are supposed to find it theoretically by calculation, not by connecting in actual circuit case. If you were supposed to do that, what you would do is actually have a printed circuit board and connect each and every element shown here as in the arrangement and short this 2 points using a wire and connect a multimeter across there and find the current flowing through that. That would be the Norton's equivalent current. So when we are computing theoretically, what we will do is just short this one and conduct a mesh analysis. So what we are doing here is having that element shorted here. Now the current flowing through this shorter element, which was initially a variable capacitor, the current flowing through that wire would be nothing but the Norton's equivalent current as shown here, and this is nothing but the resistance of the entire circuit apart from the variable element. So that's what I said in the theorem. So now we'll just see how to compute that Norton current flowing through this element by shorting this one theoretically. It is nothing but a simple mesh analysis. So now we have shorted that using a wire. Now you see there's a 2 kilo ohms resistance connected across the 2 points A and B. So this wire is in parallel with this 2 kilo ohms. Now, as a simple theory, I'll tell you one simple thing, that when a wire is placed across a resistance the equivalent resistance, that is the summation of these two resistances in parallel, is nothing but 0, since the entire current would flow through this wire itself and will not take this path, because it is offering a resistance of 2 kilo ohms. So the net resistance across these 2 points A and B, while reducing the circuit further, will turn out like this. So this is just wire, because the addition of a simple wire in parallel with the 2 kilo ohms is just again a simple wire. You can also do that mathematically by adding it. The total resistance, inverse of the total resistance, is equal to the inverse of the individual sums of the resistances. There you will see 0 appearing in the denominator, which when cross multiplied will give an answer of 0 again. So you can just mathematically verify that, and this is how the final reduced circuit is. In this particular circuit, you will be applying the mesh current. Now, before proceeding for that, I'll just repeat and tell you what I have done so far. I have taken this circuit. The variable element was this one. I have assigned 2 points. Now I'll find the current flowing through this particular element. For that, I am shorting the element using a wire, and then further reducing it into such a network, and now I'll find the current which is flowing through this wire between A and B. So this can be done by conducting a simple mesh analysis, keeping the other conditions of the circuit as same. Say for example, here it is 12 volts, we'll be doing nothing to that, it will remain as 12 volts, and here it is 15 volts, and here it is 20 milliamps. So these elements will remain the same as shown here, and here we will find the current flowing through the wire between these 2 points A and B. For that, we'll just conduct a mesh analysis and then find it out. We'll just show it how it's done. Here there are currents assigned through different loops for the mesh analysis. When a quick view over this through the circuit, you will be seeing 4 currents here. Since there are 4 meshes, 1, 2, 3 and 4 closed loops, so you'll have 4 currents, all the currents assumed in clockwise direction as shown here: I1, I2, I3 and I4. So these 4 currents we will be finding out. It is enough for us to find out just this current I3, because this is the current that would flow through this wire between the points A and B. So we have to solve for this primarily for this current I3. So in order to do that, we'll just develop the equations for any closed loop. Now we know when we apply Kirchhoff's voltage law for any closed loop, it is nothing but the sum of the voltages inside that loop is equal to 0. In fact, the algebraic sum which assigns the signs of the voltage drops. So applying KVL to the first mesh, which has the mesh current I1, what we get here is 8 kilo ohms, 3 kilo ohms and 1 kilo ohms. All the 3 added multiplied by this current creates a voltage drop, and here in the other mesh, in the adjacent mesh, we have a common current flowing through the 1 kilo ohm resistor as well, which is I4. So it is flowing in the opposite direction. Even though we have considered the directions of all the currents in the clockwise, when looking at this particular branch, you will see the current I1 flows from this point to this point, but the I4 flows from this point to this point. So it is opposing, it is creating an opposing drop. So that's why we are considering this thing as minus sign and 1 into I4, which is 1 kilo ohms into I4 with a minus sign. And this is further when you see with reference to this current, when this current flows to the circuit, this current is opposing it, so it is minus. In the same way, when this current continues to flow through the circuit, it sees the minus sign first and then the plus. So that's why this 12 volts appears to this current as minus 12 volts. So it is minus 12 is equal to 0. Rearranging, we have such a form where we are naming it as equation number 1. Similarly, we'll be having 4 equations for 4 unknowns. We'll see the same for the mesh current I2. I will explain that also, so that it is more familiar to you for assigning signs for the voltage drops and developing mesh equations very thoroughly and making it simple to you. I will explain all the meshes right now. So for the mesh 2, applying KVL for the mesh 2, what we have here is the current I2. Now the current I2 flows from here to here, but the adjacent mesh which has the current I3 flows from here to here. So according to I2, I3 is opposing it, so it is minus 4 into I3. So it is minus 4 into I3, and this is plus 4 into I3. And the I2, when it is flowing through this mesh, it is looking into the 15 volts. It sees the minus sign first and then the plus, so that's why it is minus 15 volts again. So it is plus I2 into 4 minus 4 into I3 minus 15 equal to 0. So that's the equation 2 we have. And now we apply in the KVL to the equation for developing equation for the mesh current I3. Here we see I3 is one mesh having lots of other meshes in adjacents. So here what we will see, first we will develop the equations related to I3 into 6 kilo ohms plus I3 into 4 kilo ohms, which is nothing but 4 plus 6 into I3 minus 6 times I4, because according to I3 this current again opposes, because I3 flows from here to here and I4 flows from here to here, so it is minus 6 times I4 now, and this is minus 4 times I2, because when we see this current, the I3, according to I3, I2 opposes, because I3 flows from here to here and I2 flows from here to here. So with reference to I3, I2 is again opposing, so it is minus 4 times I2. So this is the equation, plus 12, because this I3, when it continues to flow through the circuit, it sees the plus sign first and then the minus sign, so the 12 volts appears to I3 as plus 12 volts is equal to 0. So this is the equation number 3. Now we'll go to the equation number 4 developed from this fourth current, which is the fourth mesh current I4. For that, it is simply nothing but I4 is equal to 20 milliamps. This is a simple equation developed for here, because we need not write down the entire voltage drop thing as if it is like I1 into I4, then plus 5 into I4 plus 6 into I4 minus 6 into I3 and all that. We don't need to write that, because we have a simple equation here. As this is the current shown here, they have connected an ammeter and shown that already that the current here is going to flow for 20 milliamps. Okay, so this is the current we have here. So we have a direct equation as this mesh current I4 as 20 milliamps. There's nothing to confuse about this one. So we have 4 unknowns and 4 equations developed so far, and I'll just show you how to solve these 4 equations very simply in a simple method. So we have these 4 equations, the equation 1, 2, 3 and 4. There are 4 I1, I2, I3, I4, 4 unknowns and 4 equations. I'll just show you how to solve all these 4 equations very in a very simple manner. You have to go first you have to arrange those equations in order of the coefficients. So this is the equation number 1. We have I1, we have I4, but we don't have I2 and I3, so we will add a 0 for I2 and I3. Arrange the equation. Each and every equation will arrange in terms of I1, I2, I3 and I4. Wherever the current doesn't exist, we'll just add a coefficient of 0 to that current and include that in an equation, simultaneous equation format, and have a constant equated to each and every equation. So here we have 0 actually here, so here we'll be equating that as 12. Here we'll take this 12 to the other side, so we have constant for each equation, we have coefficients, and we have all the variables here. So for the equation 2, similarly, when you see here equation 2, we don't have I1, we don't have I4, and this is the 15 constant which is taken to the other side. So here we have I1 and we have I4, which is coefficient of 0, since I1 and I4 were not there in equation number 2. So in equation number 2, I1 and I4 were not there. We are having equal coefficient 0 added to that and arranging that in the form of simultaneous equation, taking the constant to the other side. So this is the equation 2 frame. So similarly, the equation number 3 and 4, we'll write it as 0, I1, I2, I3 plus I4 is equal to 20 into 10 to the power minus 3, because it is 20 milliamps. In the same way, you will observe that all these other coefficients also should be multiplied by 10 to the power minus 3, because While developing the mesh equations, you would have noted one thing, that while writing these equations, these are the values or the coefficients of the variables I1 and I2 and I3 and I4. The coefficient are the values of nothing but the resistance. Now when you see the resistance are in kilo ohms, the entire circuit, everywhere all the resistance are measured in kilo ohms. You have to note one thing here, whenever you have a circuit, whenever you are having the resistance values, have a common unit system for the entire circuit so that you don't confuse. Now here the entire circuit has a resistance values indicated in kilo ohms. So for all the mesh equations, for all the coefficients of the currents, we have the resistance values mentioned in kilo ohms. So here when you have this 12 plus 0 minus 1 kilo ohms is equal to 12, that means that you have actually 12 kilo ohms, and here you have actually 1 kilo ohms. So kilo ohms is nothing but multiplied by 1000. So this is not indicated here. In the actual equation developed, this 1000 which is here you can take out as common, and it will be a multiple of this entire equation. When take to the other side, it will become 10 to the power minus 3, because it is just from the multiplication side. When you take to the other side of the equal to sign, it will come to the denominator. So similarly for this equation, 4 minus 4, you see this 4 minus 4 is nothing but 4 kilo ohms, and applied for the mesh 2 here. This is the mesh 2, 4i2 minus 4i3. So this is a 4 kilo ohms resistor. 4 kilo ohms is nothing but 4 into 10 to the power 3. When it is taken to the other side of the equation, it is nothing but 15 into 10 to the power minus 3. So it is 4 into 10 to the power 3 actually. When it is kilo ohms here, we take 10 to the power 3 common here and take to the other side, it becomes 10 to the power minus 3 here. So rearranging the equations, we have a set of constants and we have all the variables here with a 0 added to those variables which are not existing in that equation, and arranged in form of 4 equations with 4 unknowns as 4 simultaneous equations. Now how do you solve that in just one click? It is very simple. After having arranged with the 4 sets of simultaneous equations with all the variables and coefficients, and mentioning the exact value of the constants without any confusion, you have to just watch for this mistake. You don't have to confuse with the equations showed here, because here I didn't consider the kilo ohm values. If you consider the actual resistance, it is measured in kilo ohms. So kilo ohms is nothing but 10 to the power 3, taken to the other side is 10 to the power minus 3. So please don't do this mistake, and make a note of this one while developing the set of simultaneous equations. So once you develop these equations, that is just a simple thing, you have to just solve it. So it will be solved in a one single click here. If you see here, the currents I have written down. Now how to get these current values from this set of equations? It is very simple. I'll just show you here. When you go online, you have this online mschool.com. It is simply math assistance. Here there are a number of equations in the system. It is asking, there are up to 6 unknowns. Here we have just 4 unknowns, but here we have up to 6 unknowns provided here. So we'll just go for 4 unknowns, since our set of equations is 4. You see here I have assigned all the coefficients. You have to take these coefficients and feed into these boxes wherever the coefficients, this x1, x2, x3 and x4 are nothing but i1, i2, i3 and i4, and this is nothing but the constant value which I have mentioned here. Say for example, this 12 into 10 to the power minus 3 I have mentioned here as 0.012, and for the rest of the equation I have mentioned the coefficients of the variables as here. Say for example 12, 0, 0 and minus 1. Here it is 12, 0, 0 and minus 1. So I solved this equation almost here. It is already solved. As you see, when I am writing down all the coefficient values, we just cross check for this one. It is 0, minus 4, 10, 0, minus 4, 10, and here it is minus 6, minus 12 to the power minus 3. So minus 6 and minus 0.01, which is nothing but minus 12 10 to the power minus 3. So I have written all the coefficients here, and when I click solve the system, you see the answer is displayed in a fashion where you are eliminating each and every equation by Gaussian method. You can also apply elimination by simultaneous equation solving, and finally the system online will generate a set of values here. When you see the x1, x2, x3 and x4, by just one click here, by just one click, if you click after entering all the coefficients here, you see a system of equation developed. And if by just one click here, you see I'm sorry for that I had displayed after entering the coefficient of the systems here, by just one click here after entering the system, you get the values here as x1, x2, x3 and x4. It is nothing but I1, I2, I3 and I4. Now here when you see this x1 is 1 by 375, it's nothing but when you divide 1 divided by 375, it's nothing but 0.0026 amps, which is nothing but this when multiplied by 10 to the power 3 gives the answer in milliamps. So it is 2.67 milliamps, so approximately 2.7 milliamps. So that's what I have written here, 2.7 milliamps. So again here it is 0.02425. This when multiplied by 10 to the power 3 gives the answer in milliamps, which is nothing but 24.25 milliamps. Obviously 24.25 is nothing but 24.3 milliamps approximated. Then again it is I3, which is nothing but 0.0205. It's nothing but 20.5 milliamps. So nothing but 20.5 milliamps. And I4 is already solved, since our equation itself was I4 equal to 20 milliamps in the fourth mesh. So we have solved all the currents, and the online system equation generator, here you have this online mschool.com, where you have the number of equations. We had 4 mesh equations, so there were 4 unknowns with 4 simultaneous equations, and I had entered all the coefficients of each and every variable here in the boxes provided, and click solve the system. It will directly generate the answer, and you have all the currents solved in just one single click without any error of the decimal places. That's what's more important. Now here this would be the currents flowing through the circuit in any given ideal condition. So our concern was the current I3, because I3 was the current which was flowing between the points A and B. So that is what our Norton's current, which will be representing as a symbol with Norton's current source of 20.5 milliamps. Now the next task is to find the resistance of the entire circuit except for the variable element here. So we would do that in the same fashion as we did in the Thevenin's equivalent circuit. So what we did there was took the circuit, and the element which was connected across the 2 kilo ohms, which was the variable capacitor, is now removed, and the points are named as A and B, and the circuit appears as such. Now to compute the resistance appearing across the 2 points A and B across the variable element, which was the capacitor here, to compute the resistance appearing across these 2 points A and B, you have to short all the sources and open circuit any current sources available, because we are bothered only with the resistance of the circuit across these 2 points A and B. These 2 points A and B are nothing but those 2 points across the variable element, which was our consideration, which is nothing but a capacitor. So we have to compute the resistance across these 2 points A and B. So since we are concerned only about the resistance of the entire network, we will remove all the other sources. Now in order to remove a voltage source, we will just short it, so the potential appearing between those 2 points will be 0. In order to remove a current source, we will just open circuit so that there is no path for the current to flow. So this is how we remove the voltage source and the current source. So after removing, this is how the circuit would look. See I'm sorry. So this was the voltage source, which was short circuited. Here you have the 15 volts voltage source, and here it is short circuited, and here we have the 12 volts, which was again it is short circuited here, and here we have the current source, which is open circuited. Since it will have no path to flow, so that current source is also removed. Now we have a simple resistance circuit. By reduction of a simple circuit, we will find the resistance appearing across these 2 points. Now this 5 kilo ohms resistance is as good as non-existing because it has no path connected, so this will be removed. And here all these three resistances are in series, so this will be added up to 8 plus 3 plus 1 is equal to 12 kilo ohms. The circuit further reduces to this three resistances in series, and now you have the single wire instead of the 4 kilo ohms. It was gone. Now this 4 kilo ohms is gone because, as I said a while back, when you have a simple wire connected across this 4 kilo ohms, the parallel addition will be a result of no resistance at all, so which is nothing but a simple wire. That's what you're seeing here, a simple wire. So the next reduction will be as such. See, this is what I told you. Here there's 8 kilo ohms, 3 and 1 add up to 12 kilo ohms, and this 5 kilo ohms was removed since it is as good as non-existing, since there is no path for anything to flow through it, since it's open circuited, and that is removed, and the 2 kilo ohms and 6 kilo ohms remain as such. So this is added as 12, and the 6 kilo ohms and 2 kilo ohms, that is what remains in circuits, 12, 6 and 2. So this is how the circuit gets reduced. This was as such. We are removing this one, adding these three in parallel. This is reduced to a simple wire. So this is 12 kilo ohms, 6 kilo ohms and 2 kilo ohms. This is what is appearing as 12 kilo ohms, 6 kilo ohms and 2 kilo ohms. Now the resistance across these 2 points will be nothing but the further reduction of the circuit. When you see, again there is a simple wire across this 12 kilo ohms, which is the addition of these two is nothing but again a simple wire. It is here, and this is 6 kilo ohms and 2 kilo ohms. Now you see the 6 kilo ohms and 2 kilo ohms are connected in parallel. So the parallel addition is nothing but the equivalent parallel resistance, nothing but 1 by RT is equal to the inverse, the addition of the inverse of these two individual resistance, which is nothing but 1 by 2 plus 1 by 6. The answer is 1.5 kilo ohms. Now a short way to verify the answer is that whenever you add two resistances in parallel, the resultant value of the two resistances will be lesser than the least of the two. So the least of the two is 2 kilo ohms, and the resultant value as a result of parallel addition of these two is 1.5, which is lesser than the least, which is 2 kilo ohms, and is 1.5 kilo ohms, so lesser than 2 kilo ohms. So the answer is right, and this is the resistance appearing across the 2 points A and B. So this is the resistance of the entire circuit across the 2 points A and B, except for the variable element. Now this you have to take and connect in parallel with the current source, and these two elements connected again in parallel with the variable element, because this was the element that we had removed from the circuit, and we connected back to the circuit. This is the entire reduced circuit. Doesn't matter how many times you change the value of the variable element, which is the capacitor here, you don't have to go back to the entire circuit, which was something like this, which was way back here when I explained the entire circuit, which looked something like this one. This was the entire circuit. Now in this circuit, when you see, the variable element was this. For each and every time, we need not conduct the mesh analysis or the node analysis to find the branch currents or the voltage drops across different elements. You just have to take this element separately and keep it apart and find the equivalent resistance and the equivalent current flowing through this particular element, and connect them in parallel with this variable element in a similar fashion like this, and you would result into a network like this one, which is nothing but a resistance and a current source. This current is nothing but the current flowing through this element, and this is the resistance of the entire circuit apart from the variable element. This is the Norton's equivalent circuit. It is somewhat similar to the Thevenin's equivalent circuit, which was posted in my previous video. You can just subscribe my channel to watch the theorem of the Thevenin and its application. So I hope you understood for the entire theorem and its application. If you hadn't understood, you can just drag the timeline a bit while back earlier to just listen again. Different sections are like, how did I reduce this and this one, and what's the difference between the Norton's and the Thevenin's theorem. You can watch the other video side by side and compare that, and have a clear view how to actually perform the reduction without any error. And I thank you for listening to this lecture, and until next time, goodbye.